Pleasure for me to introduce today Cristina Chiappini. Let me describe Cristina. Cristina got the PhD at the University of Sao Paulo in Brazil. After she had the postdoctoral position at the Columbia University, and then actually she became a colleague of us because she got a permanent position at the Observatory of Trieste that at that time was not belonging to INAF, I think. But after she moved to the University of Geneva, and nowadays she has a permanent position at the Leibniz-Institut for Astrophysics in Potsdam. Let me say that Cristina Chiappini is really an astonishing, fantastic scientist, let me say, is one of the main experts in the field of the study of the chemical and chemodynamical properties of the Milky Way. She's one of the main experts in the field, in the quite modern field of galactic archaeology, whose aim, for people that are not directly involved in that, is the purpose of this research field is to study the process of formation and evolution of the Milky Way. And she's a very wonderful expert in the exploitation of large spectroscopic survey as Apogee, RAVE, and she's also directly involved in the use of the Gaia data and so on. So please, Cristina, the stage is yours.
Thanks a lot for the presentation. I will share here. So once I share this, I cannot see you all. So let me just share first. Yeah. Just let me know if you're seeing the first slide. Yeah? Okay. Yes. Yeah, ok. So, parlerò in inglese, come abbiamo deciso, però volevo ringraziare l'invito in italiano. So I am very happy with this invitation. I would like to have been there in person. In the end, it was not possible. So I hope that one day I can come visit this observatory. And I would like today to give you a bit of impression. It's very difficult nowadays to give a talk about galactic archaeology because so much is happening. And so I have tried to focus, give you a big impression of what it is and how we combine the different data sets, and then choose some key topics, especially where we have been working this year, 2023, to give you some feeling of how powerful this thing is. So that's why the title is from super metal rich to very metal poor stars. We are using those as like the tip of the iceberg. They, the stars and their properties keep information about the processes involved in the formation of our galaxy and also of other galaxies in some sense. So exactly, I like to give the talk today because exactly 1 day ago or two, it was the 10 years of the Gaia mission, and they made this special logo here to celebrate that. And it's amazing that the Gaia is there already since 10 years flying. I cannot start this without here highlighting many collaborators along these years. They are in this list here. So the Gaia made this nice things to celebrate the 10 years. Give some interesting numbers and what Gaia has been done. But one of them is this 10,000 plus papers. It's really amazing if you think about that. And just as a curiosity, Gaia is in the L2 orbit around, it has done around the orbit 20 times. There are some interesting things. There are some videos around about this celebration that I invite you to have a look. So it's a nice day to be giving this talk because of these 10 years as a mark of what we did. I am not a Gaia. I'm not inside Gaia, but I'm using Gaia, and I'm very happy to be involved with this data. So the Gaia, if you go to the web page, Gaia right now has impacted several areas, but if you go in their original web page, the Gaia goal is to chart the three-dimensional map of our galaxy, and with that review its formation, the way it was formed, providing also unprecedented position and radial velocity measurements with great accuracy. And so this is like the main goal of Gaia. But of course, Gaia has made many other discoveries in the way, as you can see here, for example, even planets were discovered with Gaia. And what I work on is exactly on this first goal of Gaia, in making a map of the galaxy, and it's a multidimensional map of the galaxy, and multidimensional because we have positions, velocities, chemistry, and hopefully also age for some targets. So this is a huge impact since the last mission that was Hipparcos. So from Hipparcos to now, you start from 200,000 stars with 1 to 2 milliarc second precision accuracy in parallax, and here you go to 100 times more accuracy and almost 2 billion objects. And this is a slide I took from David Hobbs, where he was presenting at the ESA Voyage 2050, our ideas to for the next Gaia, which will be hopefully the Gaia near-infrared. We'll come back to that. So Gaia near-infrared, this would be what Gaia near-infrared would see. So we'll see many more targets around the midplane of the galaxy. Here you have the density in a square degree, number of objects per square degree. And if you, this is explaining to this article here, but when you see the game between Gaia and Gaia infrared, you could think about something like this. This is the projection on the sky. And sorry. And here you see that maybe, that's what we believe, even 10 times more data than Gaia in certain regions, a factor of 10, and maybe even more in some region of the galaxy. So the Gaia infrared would be going into this region where Gaia cannot go, and then we'll be probing hidden regions on the Milky Way. We'll improve the proper motion of the stars and reset what is called the optical reference frame. So it's crazy to be talking to you about Gaia infrared, which is, if it happens in 2050, not before, but we will have a very important impact in the science we can do for the inner galaxy. Well, the young people hearing could do, because I think by 2050, it's not for me. But maybe we could be talk about 8 billion stars. Okay, but why such a huge investment in galactic science? Nah? Many times I hear, but the Milky Way is just one more galaxy. So I like to show this, that we have challenges both when we study other galaxies, like a spatial resolution, age resolution, and luminosity weighted quantities. That's what we mostly get from all the studies of other galaxies. While the challenges in the Milky Way are different, we have been having a challenge to cover enough volume, have age precision at large distance, and to go through large extinctions if you want to study the bulge. Our challenges are different, and therefore the advantages are also different. And so while in the other galaxy, you not only cover a large volume, but you also have the diversity of galaxies, and you can study things more easily in multi-wavelength way with gas and stars. In the Milky Way, here on this side, you have something that's very important, because you have the detailed chemical properties of the individual stars, the ages of individual stars, and their kinematic. And so you can really have this multidimensional space where you can work this information and go back in time in the Milky Way to really understand its formation and the main processes that have happened, such that, for example, we know we have been hit by a galaxy 10 giga-years ago, which was quite massive. So this kind of story about our galaxy we can show. Now, of course, if we know with this detail, if you are sitting here as we are going to be today, you of course will learn about processes that have very important implications for what we understand about other galaxies, and especially about disk galaxies. So important breakthroughs that happened since 2010. So now in the last 10 years, let's say, is this, that we have improved volume coverage. We have this, what we call 6D phase space information, which means 3 positions, 3 velocities for each star. And we are starting getting ages with high precision and also distance. And so I like to say that in the last 3 years, it was not only Gaia that made this difference. Of course, Gaia is huge, but two other things also contribute to what we can do today. And one is the use of astroseismology for red giants. Astroseismology, people have heard about it, usually linked to finding planets, and the missions like Corot, Kepler, K2, and TESS, and Plato in the soon to come, which the main goal was to find planets. But of course, we can also use astroseismology that this is doing, especially for Kepler, which is long observation series of photometric series, so from which you can determine masses and radius, and then infer ages for very far away objects. That's very important because otherwise we are doing ages from isochron age, and then doing that, as you see, then we'll be more in closer by volumes where you can reach with the telescopes we have today. You can reach the main sequence turn-off and the subgiant branch. So this is an important additional information coming from astroseismology that will help also the information with Gaia. And the third thing I like to point out, among the several spectroscopic surveys, all of them are important, but Apogee has played a special role because it's an infrared spectrograph from Sloan, and has made us able to go deep into the galaxy and peer the dust and go and see the bulge. And so Apogee combined with Gaia is really also a great thing. So let's dive into this mapping of the Milky Way then. The Gaia data that you saw in my first slide is just the beginning of the story, because you have to combine it with other information so that you can get from that data precise distance. You cannot just invert the parallax that you can have only in a very small volume if you want. But at the moment that you have extinction and other problems, and that you get into a larger volume and the uncertainty in the parallax increase, you need more. And there's a whole discussion about that. You need to combine this with a Bayesian approach where you also enter with complementary information, which could be, in this case that I'm showing you, we did that already in 2019, but now we have an update combining the Gaia EDR3 with other photometric bands. If you don't have spectroscopy, you can already get some hint of the distance. So you can go from a plot like this, which is just showing the density of these targets, that for which we run our code, our spectrophotometric code called StarHorse, and then you can go to what we really want to see, which is in the three-dimensional thing. So here you have X and Y, like you're seeing the galaxy from above. Here you have Z and X, like you see the galaxy from the side. And look, the scale is very big, 40 kiloparsecs. You see the Magellanic Clouds, the Sagittarius dwarf, and then you see also here in this part is the galactic bar. Of course, because it's in the optical, if you look it on the side, you're not going to have here, you're not reaching the bulge here. For that, you need Gaia infrared or some odd spectroscopy survey, which is what Apogee is going to do for you. So I want to say that this is a run we did from StarHorse using Gaia DR3. We got distances and other parameters for everything that's brighter than 18.5 in G. And this makes already from 400 million targets, we provided good, where we are happy with our distance and extinction for around more than 300 million targets. This we always make public as a group. This is data that you can always find in our StarHorse webpage inside the AIP, which is my institute. And there you can, we give some explanation how you can use the data, and if you need anything, you can contact us. So this is only photometry plus Gaia. Now, we can also combine the Gaia with photometry and spectroscopy if we do have spectroscopy. So we do have the spectroscopic surveys that have been already on the way before Gaia, which are, for example, LAMOST, Apogee, Gaia ISO, the SDSS tool, the Segway, the Gaia RVS, which came with DR3, which also gives spectra for the bright targets, Rave, and Gala. These are the ones. So what we did recently is that we combine now the Gaia EDR3 outputs with all the spectroscopic surveys, and we managed to provide for around 11 million sources covering all the components of the galaxy, and combined with the parallax of EDR3, for which more than 70% had very good parallax, plus extra photometry, we determined these parameters. So this is then our Star Horse plus spectroscopic data set. And of course, for a portion of it, for the main sequence turnoff and the subgiants, we could then estimate ages, isochrone ages. So if you look now for this spectroscopy plus photometry plus Gaia map, so similar to the one I showed before, the Y and X here from above, here I indicate where the bar of the galaxy is, you immediately see that the apogee is the one that mostly covers this part of the galaxy where the bar is. What is important is that while are we doing this? We are doing this because we need a precise distance. And once we have precise distance and the radial velocity, we can then compute orbits for the stars. And that is very important so that we can better understand the mass that is the Milky Way. And so this again, this data set we also made public in the same web page, but now is this project here. Again, there you have the description of our data model, how to get the data, and so on. One very important thing here is that what we haven't done, and this is still to-do list, but will be done by other groups, I guess, is that we haven't homogenized the input of the spectroscopy. So we are using the spectroscopy coming from each survey pipeline for the public release. Okay, so, but anyway, we make this public. So we usually make these data sets, and of course, we are doing this also to prepare for the foremost survey. But now here that you have an idea of the map, so where we can go only photometry and photometry plus spectroscopy, I can then focus because on some examples, otherwise it becomes too abstract. When you have the 6D phase space information plus chemistry plus ages, then I will focus today on this situation where you also have ages. Okay, so I'm going to give you the first example when you go to the very metal poor. What this data set enables. Of course, there is a lot of people working on the metal poor environment. There is where you are mostly outside from the disk, usually in these works, and therefore is easier because you can see more clearly the not yet totally phase mixed debris of stuff that being accreted to our galaxy. I'll give you an example. So here in this paper, Queiroz et al. I just show you where we combine photometry, Gaia, and spectroscopy. Let's take one of, in that paper, we have several plots of the alpha over iron versus iron plot, which is a typical plot that we use in chemical evolution, because something at high alpha usually tends to be older, and younger, and low alpha tends to be younger. But this is a general thing, it's not true all the time. But here, and there we have for several surveys, but here I cut a piece just to show you what we have for Sloan as Segway survey. There you have a situation where you have a low resolution spectroscopy, but you have a survey that goes deeper. Because you have low resolution, you can go deeper. And you see that the ages that we are getting is showing an excess of age here at lower alphas, right? And so this is showing that you have something, a debris entering here that's not the thick disk or things that we usually see here in this more high alpha. And then we look to that in the phase of validation to see if our aids were working more or less. This is for a small volume, as I said, where the subgiants and the main sequence turnoff are visible. And just by going there, we could see that just by taking this file, we could already select Sagittarius stars from the stream, Sagittarius streams, I'm showing you in a while. And immediately we got an enormous number of streams at the very metal poor situation, including more than 200 very metal poor stars, so stars are below -2, and even 7 globular clusters. So let me show you one thing, how we selected those. So this is a very typical thing nowadays. You can compute the angular momentum, and you can plot these things Yeah, here it's a bit out of place, but if you take this dynamical parameter, the JZ, which is, sorry, there's somebody entering. You take that here, I'm showing you stars that are more in polar orbits, so not radial orbits. If I had plot more stars in radial orbits, you would see more Gaia Enceladus. But here to show you Sagittarius, if I am plotting this kind of plots, I can very easily select where the Sagittarius stream should be. And here you see this in another plot as well. So once we select that in these metal poor data sets, you can see that here, for example, you have the Z and X in the galaxy, so the height above the midplane and X or Y. And in gray and in magenta, you have a simulation of the Sagittarius stream. So when Sagittarius passed near the galaxy, the stream of stars that it had left. And if you see our data over, you see that if this is the galactic center and we are sitting here, we are getting stars that are nearby us, from where the stream is nearby us, and we have the possibility, our stars is getting both the trailing and the leading arm. And that was amazing because we could show with this data set that I am just telling you, that has all this information, phase space, and because we have the orbits and the metallistics and the alphas, we could show that one arm is essentially more enriched, more metal poor than the other arm. And this could suggest that Sagittarius had a gradient before it was falling in our galaxy, which is amazing. If you think you are sitting here next to the sun and you can tell something about the story of a galaxy that has already merged with us long ago. So this I find really amazing. And one other thing we can do is like if you do the alpha iron versus iron, and here in the back, these things we plot the segue. And here is the thick disk, I mean, the upper part of this alpha iron versus iron plot. And now I can select also the Gaia Enceladus, which is this big galaxy that collided with our galaxy around 10 giga-years ago. And also the leading arm and the trailing arm of Sagittarius. And you see that each of the things, our thick disk, the Gaia Enceladus, and the leading arm and the trailing arm of Sagittarius, each of those have different sequence in this alpha iron versus iron, indicating different star formation efficiency, different star formation histories that we can pick it up by studying orbits plus alpha and iron. So this is very nice. Another thing that was interesting is more specific is that you see our data here. I'm showing you here the iron from -1 to -3. We are really metal poor thanks to this data set from Segway. And in this metallicity range, it was thought that also Sagittarius wouldn't have what we call the carbon enhanced stars. And here we do find some carbon enhanced stars. And so we provide also the first age estimates for the individual stars of Sagittarius, because we had some turn-off subgiants for which we could get isochron age, and it's something around 11 giga-years. And we confidently show that we do have carbon enhanced stars in the Sagittarius stream. So this is just gave you an example of how powerful this is, because this is a one survey inside the paper of Kairos 2023. But why we choose that? Well, because that had the powerful to show this, because we know it was deeper. We are seeing an excess of old stars at low alpha, so you go for it. That's what I wanted to pass you the impression of the situation now. The situation now is that we do have information a lot, and we can focus on different samples depending what we are going after, right? Because not all samples have everything you need. The sample I just showed you lack more detailed information in chemistry. Okay, another but increased a lot your number of stars metal poor, very metal poor, below -2 even, right? -2 means 1/10,000 metallicity of the sun. Okay, so we can go the other extreme, which is also interesting. And that's where the apogee can play a big role. Okay, so why did I say here super metal rich here and there? What's the super metal rich star? So solar is 0 in this scale of FV/H bracket. So solar is 0. And 0.2, above 0.2, we start calling it super metal rich, because it is in the sense that is almost 1.5, 2 times the metallicity of the sun, And we know that the interstellar medium here, this position is more or less like the sun. So this star supermetal rich makes easy for us the situation, because we know that in our galaxy, many stars are born in one place and move to another place due to secular process involving radio migration, or also mixed with accreted objects like you just saw. I mean, those stars are from Sagittarius and are here. They are mixed in the sky, right? So that's why the supermetal rich are nice, because you know they for sure migrated. And then one way to prove this is if you now look here. Now you are sitting at the solar vicinity, okay? And look into the Kepler data, for which you had the complement information from Apogee. And for this data, we could get seismic age in this case. These are giant stars. And then if we plot the number of stars in the solar vicinity versus metallicity, we see that these stars here above 0.2 solar metallicity, they actually tend to be intermediate old or very old. So in a chemical evolution where you enrich the interstellar media along of the time, you wouldn't expect that you would expect that the end of the metallicity point is the younger stars. But we know we haven't get to 0.4 in metallicity. So we know, no, I'm telling you that there was radio migration, but you say, well, why should I believe? Well, the ages make you believe that these stars they are not the end of the chemical evolution at this position. Otherwise, it would be the young stars. And as you see, in fact, the young stars metallicity distribution stop at around 0.2. So this gives you an idea that there are the supermetal rich stars in here, they are also very old. So the first question is, where did they came from, these supermetal rich stars? Okay, there we can also now use all the data sets to explore this. And this is the bit more complicated part of this talk. So first, let me show you. I show you we had run Star Horse here with Gaia, and then could do the 3D maps. And you see here face on and edge on our galaxy. We have in these maps, as I show you, more than 300 million objects. In this box around the bar, we have something like 30 million stars. But now these 30 million stars do not all have spectroscopy. When we ask for stars here, but with spectroscopy and Gaia information, we are down to 30,000. Still is a lot, 30,000 from Apogee. Okay, when you go to this box, it's the same box I'm showing here, okay? So this box here, which means 0 here is the galactic center. And we are around the 2 parsecs, or 2.5 parsecs, kiloparsecs from the galactic center. So really that inner box. If I go to that inner box and I see what the Star Horses give me for AV, so extinction, I see that I have a very high extinction. Even though I'm looking the H-band, I have a very high extinction in the middle of the plane. But still, Apogee can get data around here, and that's where we're going to explore. And we have around 30,000 stars, as I said. But we need to clean this, because I have in a bit of foreground disk stars. And the way we use to clean, because we are afraid that maybe we could have systematics in distance, we then wait for EDR3, where we have an improvement for this sample sitting there. We have an improvement in parallax error and improper motion, especially. Right? From we had the Gaia data release 3, you had an increase in a better proper motion. So what we could do is that, first of all, I would like to say that before that, what we can do is that same alpha variance plot I showed you before. You can do this alpha variance plot now, not only in the solar vicinity, but at different positions in the galactic with respect to the galactic center. So here's the inner beam towards the outer beam, and for different heights above the midplane. I don't want to discuss this today, but I wanted to focus here in this inner square. This inner square is this box I'm talking you about, around 20,000 stars here in the inner parts. So first of all, you have a radial velocity, and you can do the kinematic plot of that region. And for the first time, we had such a precision that we could see this pattern, which unveils this quadrupole feature that is characterizing the streaming motion induced by the bar. And this is also seen in some simulations. This shows that your distance is good. But on the other hand, we could use the proper motions and define an even better sample to go very much inside the galaxy. And that's what we call the reduced proper motion, which is this equation. And then we pass from the distribution of the box that I told you in distance was like this. And once we use the reduced proper motion to define a more innermost sample, our distribution in distance is more centered into the inner galaxy. That's what we want. And then I go forward now only with the RPM selection, which is reduced proper motion inner galaxy. Now we will go, the price to pay is that we will go from 20,000 stars to 8,000, unfortunately, right? And so some thousands. And what we will do now, here's a bit complex, just bear with me a little bit, is what we're gonna do, we will look to these 8,000 stars. Because it's difficult now, you cannot tell me what is thin disk, what's sticky disk, only based on chemistry. It doesn't work anymore like that. It's everything very much mixed. And in this inner 4 kilopars, there is a coexisting populations are all at the same place. So you have a bit of disk, a halo, thick disk. And so what we do, we analyze all that sample in a families, let's say, kinematic orbits. Like I plot them in a Z-max, the maximum height the star reach in the orbit, and the eccentricity of the star, of these orbits, and I throw my sample here, and then immediately, it's amazing because we are computing orbits for stars that are in the galaxy center, okay? Very much in the inner parts of the galaxy. We couldn't do this before. And then here you see immediately, if I color this by iron, you see you have a concentration of metal-rich stars very much in the plan. Stars that do not reach more than 1 kiloparsec from the mid-plane. So they're really confined to the mid-plane. They are more metal-rich. And then you have more poor stars everywhere. Now, we then look into all the chemodynamical properties. Now, the chemodynamic for each D square, for each of these little windows that I'm making here, I have all the information of chemistry because now I'm on apogee. So I have alpha over iron versus iron plus many other things. That's why I put here 7D plus dimensions, right? And when I do this, I see that in there, I see an inner thick disk, an inner thin disk, and an old spheroidal bulge. Otherwise, you wouldn't see it because the bulge is buried in the middle of the disk. So you would think that there is no spheroidal bulge if you do not do this. I'll just show you very briefly if I say that the same 9 windows we were looking before that came from this plot here, but now I'm looking there alpha over iron ratio. And here, just call your attention for this low part. Here is the part that the stars are on low Z-max orbits because this I'm showing up to 1 kiloparsec here. And you see that, forget the color for now, these stars here are the stars that are in cold orbits in inner galaxies, and they can migrate. So this would answer our question where these supermetal-rich stars came from. We will go down and look in a while. While here, the stars that are in high eccentricity, and if I leave the down part here and I go for stars that are a bit more high in the orbit, I reach this, what I'm calling spheroidal bulge. And of course, I always have accreted debris that I can figure out from the low alphas that they have at the same metallicity. So this is where the spheroidal component appears. And I now take this part here down on the plot. So the stars that are in cold orbits, they're inside. And I look to their metallicity distribution. And what do I see? I see an enormous quantity of very metal-rich stars. These stars are peaking above 0.2 dex in metallicity. So these are our candidates for migrating here at the solar vicinity that we saw before. And if I go now to the other group and I go up, I see that the metal-rich population there start to decrease. So the stars, the more metal-rich stars, are really more on cold orbits. But the metal-poor stars already existed even down there, and they become very pronounced as I go up in Z-max. And that's where I see most of the old bulge. And that's where we see the oldest stars buried in the middle of the Milky Way. But I don't have age right now, right? So I am arguing that there we are seeing stars that were formed equivalent if you go to another galaxy at redshift 5. So, but what about the ages? Now, if I take this plot here where you show in in the distribution sky L and latitude and longitude, the extinction, the median extinction have here I took from another work. And I plot here some globular clusters of the bulge. For these globular clusters, we managed to have data and photometry. And if I plot them here, they are also tracing this very old population. These globular clusters are very old. We have estimated their ages, and they lie here. They are stuff that are almost 13 billion years old. So together with these very old stars, we believe are in the bulge. Why is this interesting? Well, because also in high redshift, you start seeing these clumps, these high clumps of star formation that people think can coalesce and go to the bulge. And this would be the local counterparts of what we're seeing there. Where are them? You see, are they these local counterparts? So if we have to look for them, we have to look either to a very old disk or to the inner parts of our galaxy. There are some recent models about that, where they call the clumpy bulge. Some simulations suggest that the clumpy bulge should have this, should show like this in oxygen of iron versus iron, while what we see is this discontinuity. And they suggest that our data goes against the model, but actually not, because here you have everybody in. And as I just showed you, if you wanted to compare with the clumpy bulge, so the pristine bulge, you have to look to these stars that are tracing it, which is not the whole thing, but it's only that upper part. And so by the orbital analysis, you know that is this plot here, you should have compared with that. Here is the most old bulge, and look how similar this is to what you see here in oxygen over iron. So this is very interesting, and we are going now to explore more this metal poor part of the old bulge. So now, I just told you the supermetal rich migrate. We know where they came from. We have seen them in the inner parts of the bulge, but we can do better, right? So how they migrate? The idea is that many of them are pushed here by the bar. And so for that, we need a different data set, because what we are going to do is that we're going to use a large sample of supermetal rich stars at the solar vicinity for which we can get ages. And for that, we are using a new data set that is using the Gaia DR3 information with radio velocity, but improving the stellar parameters using the hybrid convolutional neural network technique to get better atmosphere parameters. And this will give us an opportunity to see things that you would not see otherwise if you use only what has been published before. And I'm going to show you, as this is the last thing I'm going to show you. This is a very recent letter we published, where we now are going to use this RVS, this data set of the RVS plus a star horse again. And then we have 170,000 stars here just sitting. Now here is different. This is the sun. This is around us, 1 kiloparsec around us now. So before we were there in the galaxy, in the inner galaxy, now we are here to see about these high metallistic stars. Did they come here? How did they come here? And now we see that they are linked to the properties of the bar, and they can give us an idea about when was the last moment of very high activity of the bar, just by looking to the metal-rich stars. And I'm going to show you this. This is just to show you that now we are going to analyze for this sample the subgiants and the main sequence turn off, and we have mostly stars in the disk, low alphas. So let me jump this. So what we see, I'm just focus on this. If we plot the metallicity versus the age it is not an age-metallist relation, because here I'm plotting only the most metal-rich stars at each beams of age. That's what this plot is. You see that suddenly you have a drop of these metal-rich stars. It's like after 3 gigayears, stars younger than 3 gigayears are not arriving here anymore from the bar, you see? And therefore, we suggest this is the time where the bar essentially shut off. Stop sending us the stars. You can say, oh, but do they need more than 3 gigayears to arrive here? No, they need actually less. And so what we think is that this drop, this sudden drop, you have a general behavior here that you can have had other epochs of bar high let's say, formation or buckling. And here you're like achieving the last one because you have this drop. If you don't believe in your ages from mean sequence turnoff and subgiants, we check that also with, and we got a very similar result with a different sample, much less statistic, is the sample that I told you before, Kepler plus apogee. And there again, you see, so here the ages are seismic ages for red giants. Here the ages are subgiants and mean sequence turnoff ages from isochron ages. And in both, you see this drop at around 3 gigayear. Now, the cool thing is that if that is the case, simulations show that when you have this very high activity bar moment, or the last, because it lasts only 1 gigayear, then you could induce an extra star formation, because you essentially perturb a lot the disk and you form stars as a cause of that event. You not only send the stars here, but you also provoke more star formation in situ. Do we see that? And we think that we do see that. And this is like, this now is the age metallicity relation up to 10, 12 gigayear plot here. And you see here is alpha over iron versus age, and here's metallicity versus age. And you see that you have this blob here. You have a blob at around 4 gigayear ago, right? And we are suggesting that this is linked to the metal-rich stars and to the activity of the bar. Look how crazy this is. This can get. And you see, for this population, a slightly increase in the alpha over iron, which is a typical signature of bursting. When you burst, you put in the medium a lot of high alpha stars. And so you have this slight increase in alpha over iron. So I will finish. I think I have another 5 minutes, if I am not mistaken. Yes, I spoke 40. So I'll use these last 5 minutes just to show you a little bit where we want to go. So the examples I gave you show the power of having a large volume covered or large statistics, even if the volume is small. What's the advantage of the sample I just showed you now before? The RVS sample together with the CNN and the thing that is the statistics. We got a large number of metal-rich stars. The super metal-rich stars are rare objects. So you need a large statistics to get them. And we got a large number of those stars in the main sequence turnoff and subgiants, so we could get the ages. So each sample has its big thing. So therefore, thinking about all that, we are preparing for the formidable LOR, which is our survey within Foremost using low resolution, low medium resolution, 7,000. That's why I'm also checking my data in slow and segue and so on to see the power of these more low resolution things. This is a big collaboration that we are doing. We have more than 60 people in our survey. I am the PI together with Ivan Minshev. And here is more or less how we intend to cover the galaxy. Here is the bar. And because we are in the south, we can provide a fantastic coverage of the inner regions of the galaxy. We will have 2 catalogs called dynamic and chemical disks that cover a large portion of the disk. But then we will have the extended solar vicinity, which is really this that takes the creme de la creme of Gaia, because there you have the best parallax. You can go to very exquisite velocities and so on. So you can do crazy studies both with kinematics, but also with age. And then we are going to have an extra sample, which is called the bulge inner galaxy, that covers the region bulge inner galaxy. And in there, we're still going to have another sample that's called the bulge deep. And so essentially, why we need that? Here is again the X and Y distribution of the current spectroscopic surveys, and there is a lack of surveys in this part in the south. In the north, you have a very large cover by Lamost and Apogee, because Apogee had a lot of stars in the north. Later, there was the Apogee South that did here. You have some also come from Slower 5, and will be complementary to what we're going to have here from our survey in this part of the galaxy. To give you an idea, currently for the bulge, specifically for the bulge, if you look here in the latitude and longitude, just now focus on the bulge, you have the BDBS survey done with the dark energy camera by Mike Rich. This is sampling more than 200 square degrees with photometry only, and they have 250 million stars there. And we are complementing this with our bulge inner disk. But look, our bulge inner disk footprint is that big. And then on the top of that, we will have the very metal poor catalog, the one where we are following up the pristine inner galaxy survey stars, and also the bulge deep. The bulge deep is one where we are going to cover more this part here of the DBS, which is the southern part of the bulge with less extinction. Here I'm just showing you that despite we have a low resolution, the other side of the coin is that we can go deeper and we can have this very large wavelength range. And in this very large wavelength range, we have a lot of species that for which we think we can get some ideas of chemistry also from low resolution spectrum. That's why we are doing several works in this direction, explore machine learning over this large wavelength range. So I finish here my 45 minutes by saying that my key points are that Gaia plus spectroscopy plus photometry made it possible that we have precise distance. And this precise distance are showing the good example of this is this velocity quadrupole I show you in the middle of the galaxy in a region very hard to get before, but thanks to Apogee. And also, for example, in this enlarged sample we got for Sagittarius stream, getting even ages for those stars. The bulge can now be studied in orbital chemical space, something that was difficult before. And we do see hints of the pressure support component, which is the old bulge, as we argued. The objects confined in the innermost 4 kiloparsec show a metal-rich thin disk that I didn't have time to enter into the details, a thick disk population, and this velocity with this population, very high velocity dispersion, which we call the old bulge. The globular clusters in the bulge give us an idea that the stars in the old bulge are really old if the globular clusters are part of this. And we are talking about ages of around 13 billion years. So we are at redshift 4.5, 5. And so we are complementing what we see at high redshift. A lot of results are still coming, very interesting about the disk. And also, I show you that in the innermost part of the galaxy, we have a reservoir of very high metallicity stars, around more than 2 times the metallicity of the sun. And this can be pushed here by the bar. And by studying now with nearby sample, this moment, nearby sample, but with large statistics and very precise parallax, like is the case of the RVS, we can then even have an idea of the age of the bar and so on. So it's really an amazing, I choose just a couple of results to give you an idea, but it's an amazing time. That we are preparing 2 conferences. One is a conference in honor of Francesca Matteucci that will happen in July 2024 in Italy, near Napoli. And the other is a Yahoo symposium on stellar populations that's in honor also of Beatriz Barbui, and who has contributed a lot in the field. And this will be in Brazil in November, and we are still trying to get a good hotel for the meeting. Thank you very much.
Thank you, Cristina, for this very interesting and complete talk. There are any questions from the people attending? Okay, Sergio, please.
Ciao Cristina, Sergio Cristallo.
Ciao.
I have a question which is not directly related to your seminar, but I